Okay, so this question is asking us which compound is used as a standard for NMR chemical shift measurements. So the first thing we need to clarify here is what exactly an NMR standard is. And a standard is a substance that's included in sort of every NMR sample that's going to be put through an NMR spectrometer to give a well-defined peak that everything else is measured relative to. So NMR doesn't have like any absolute peak values, they're all measured relative to a standard that's included with the sample. So the first thing that we need to check is that all of these all of these compounds actually produce a peak in both carbon and proton NMR. They're the most common ones. Other types of NMR might use a different standard to the one we're going to talk about here in this question. But the first thing we should be checking with these is whether they actually produce a signal in both carbon and proton NMR. So the first one that's drawn my attention is D2O. This doesn't have a carbon in it, so it won't produce a peak in carbon-13 NMR. In the same vein, this is deuterated water, so D2O rather than H2O. Also, no peak in proton NMR, because D is the same as heavy hydrogen. It's just got an extra neutron, which is sometimes called heavy water, deuterated water. D, in the same sort of idea, we've got tetrachloromethane here. This is not going to produce a peak in hydrogen NMR. There's no hydrogens in this compound. We're not going to get a peak in hydrogen NMR. Same problem with this. This is deuterated trichloromethane, otherwise known as deuterated chloroform. And this does have a carbon. It has deuterium rather than hydrogen though, so this is going to have no peak in hydrogen NMR. And in reality, all three of these, B, C, and D, are actually good NMR solvents. It's very desirable for a solvent not to have a strong peak in your NMR spectrum. So it's actually good that these don't produce peaks most of the time because we use them as solvents. So the one that's left over is tetramethylsilane, and this is a really good NMR standard because we have lots of peaks, lots of carbon atoms, hydrogen atoms in the same environments. So we've got 12 hydrogens that are all in the same environment. We've got no adjacent hydrogens that are going to cause any splitting, so this is going to create a singlet peak that's very intense from a small amount of tetramethylsilane, because we've got those 12 hydrogens in the same environment all contributing to the same peak. And the same is true with carbon. We're just going to get one peak that's going to be quite intense because we've got 4 atoms all in the same environment. So here the answer is going to be A.